Hello. On behalf of BIC Magazine and our sponsor, Mistras Group, I'd like to welcome everyone to today's webinar on how to utilize wireless sensors to track corrosion and erosion in piping and vessel walls. This is Brady Porsche from BIC Magazine. Before I introduce today's discussion, a few brief housekeeping items. You can resize or hide any of the windows in the webinar console. For example, you can maximize the slide window for best visibility. Across the bottom, you will see widgets to access resources related to the webinar, including a Q&A link to submit questions anytime during the presentation. The speakers will answer questions after delivering the presentation, and will answer many of the questions they did not have time to address by individual email in the coming week. If you experience any technical problems, go to the FAQ help page at bicmagazine.com and select Webinar Attendee Help page under the Events menu. Before we get started, I'd like to say a special thanks to our sponsor, Mistras Group. Mistras is a leading one-source global provider of technology-enabled asset protection solutions used to evaluate the structural integrity of critical energy, industrial, and public infrastructure. Mistras uniquely combines its industry-leading products and technologies, including 24/7 online monitoring of critical assets, mechanical integrity and non-destructive testing services, destructive testing services, process and fixed asset engineering and consulting services, and its world-class enterprise inspection data management and analysis software, PCMS, to provide comprehensive and competitive products, systems, and services solutions from a single source provider. And now it's my pleasure to introduce you to today's speakers. We have Larry Gocknauer, National Sales Manager for Ultrasonics Products, ASNT Level 3 for Mistras Group, and Sam Ternauchek, Vice President of Online Monitoring for Mistras. So without further ado, I'll now hand it over to Sam Ternauchek.
Thank you, Brady. I too would like to welcome everyone here today that's taking the time to listen in on what we have to say about one of our new products. And as we said, what we are looking at is a system that gives us the ability to track and analyze thickness data remotely. So let me get into the presentation. And as far as the presentation goes, what we'll be talking about is a little bit of an introduction, again, to what we're talking about. Talipray is the name of the product, and you'll see it referred to throughout the presentation. So we'll give a little bit of an explanation about that. Talk a little bit about what's involved in doing an installation, what's required in terms of hardware and support. And then Larry will take over and talk about some of the software capabilities and open it up for answering questions, et cetera, at that time. So that's kind of the overview of what we wanted to do. As the introduction, let me just give you a little bit of background on that. Most of you know Mistras Corporation as a service company. That's primarily the visibility we have in marketplaces. But we also have an instrumentation division, which is responsible for designing and developing different technology, instruments and technology. In that group, we are the largest provider of acoustic emission equipment in the world. We have several different ultrasonic systems. We have vibration equipment. So there's a variety of offerings we have from our products group. Now, about 10 years ago, in conjunction with the Department of Transportation, we started developing wireless technology for acoustic emission products. These are intended to be installed in infrastructures, bridges, buildings, etc., and used with acoustic emission technology to monitor these structures remotely. Well, a few years ago, we started talking to some of our customers, and they suggested that since we had the technology for several years in the acoustic emission field, why not transfer it over to the ultrasonics field also, not only as a monitor, but of a way of doing analysis with the information we got. So the result of that effort is, as I said, the Calibre system. And let me give you a little bit more detail now about what it is and how it works. The main concern here is corrosion assessment. Corrosion is a multi-billion-dollar problem throughout not only North America but the world, and pretty much everybody has to deal with it in one way or another. The conventional way most often used is manual periodic inspections. This is where the technician goes out with an instrument and a transducer, takes a measurement, comes back, records it, and we trend it over time. What we are now doing with technology is installing permanent ultrasonic thickness transducers and using technology to remotely transfer the data and monitor that data. So Calibre is designed to conduct ultrasonic wall thickness measurements and to determine the integrity of assets, thereby reducing the susceptibility to damage and potential safety hazards, etc. So what we want to do is look at technology to help us improve on what we have been doing for a number of years with manual ultrasonic measurements for our corrosion assessment programs. Here's a good old level 1 technician. He's got his ultrasonic thickness gauge. Looks like a ultrasonic system that gauge that Mistras actually makes, called the Pocket UT. And as I said, it's a fairly economical way of collecting large amounts of thickness data. We use a lot of the thickness data in planning our resources for maintenance and repairs. And so thickness data is a very important part of our overall strategy for maintaining and containing corrosion. So it is economical, there's no question about that. It can be used in a large number of areas, various materials, various thicknesses, temperatures. So it lends itself nicely to a wide range of applications. Usually it's pretty accurate. We'll talk a little bit more about that in a minute. But again, it does give us a good representation of what the thickness is. And over time, it does help us trim the thickness and the effects of corrosion on the asset. Typically performed by a level 1 technician. Most companies will use the UTT level 1 classification as one of the early certifications for new hires. Obviously, they do have to get a significant amount of training and oversight according to their TC1A program. But it's typically performed by a level 1 technician. And as I mentioned, it's been in use for a long time. It's got over 70 years of history in industry. So there's a lot of information. And as I mentioned before, when it's done correctly and the accuracy is very good, it is a very useful planning tool for maintenance and repairs. Now, there are some things that have to take into account when you're doing manual UT, and all of these tend to affect the accuracy. First and foremost, we need to be able to calibrate the equipment to the material that's being tested. If it's not calibrated to the correct material, you'll definitely get the wrong reading. So Knowing the material type and calibrating the material type is a very important aspect of manual UT. And you've got to send somebody there to make the measurement. Now, if it's an easy access place, then that's fine, but that's not always the case. So getting access to the work area in many cases can be a major consideration. Another critical part of getting the measurement is surface conditions. We need to make sure that the surface conditions are adequate for getting a good reading, and we're taking the reading in the same place. Just a small change in the location of the reading can have a significant effect. So we need to make sure that we know what we're testing. We need to make sure we can get to it safely. We need to make sure that the procedure that's being used is correct and that the person doing the testing is qualified and certified to perform that particular test. So there's a number of variables that can come into play that can affect the UT thickness readings. And over the years, there's been a lot of improvement. There has been better instrumentation. There have been improvements in training and oversight of trainees. And we have a more reliable technique now than probably any time over the past 70 years since it started being used. But it doesn't change the fact that from period to period, we can see variations in the readings. So as you can see on the right-hand side of the slide here, it's not untypical to have some sort of variations in readings from period to period. In this case, if you look at the chart, you know, it's kind of indicates that there may be little or no corrosion going on, but over one particular interval, it's not necessarily that obvious. So there are some things that still come into play that can affect the accuracy of the data from reading to reading. Another issue here is that if you're taking readings every 5 years or even every 2 years or 3 years, you can have some issues arise in the process that could increase the rate at which corrosion or erosion is occurring during that particular time. And if you're taking measurements every 5 years, you're not necessarily going to be aware of those quickly, especially if they happen just after one measurement. So it's difficult with manual measurements to identify a problem at an early stage. And we're also only getting a reading every 5 years, so we're kind of taking a snapshot of the conditions at that one period of time and then not aware of anything that may be going on at that location for a period of time, which you know, can be a problem also. So there are some limitations: the accuracy of the data, the long time between readings, difficulty of early detection, and some limitations in how much information you're going to get. So that's where the permanent sensors come into play to help address some of these problems. With permanent sensors, you're attaching them at the time of installation and they stay there. There's no removal unless there's some sort of maintenance has to be done with that particular area. But you put them in place and they stay in place for as long as you want to have them there. Since you don't have to deal with a lot of the variables that occur with the manual readings, the accuracy of the readings are very good. You're taking the same reading, same transducer, same position, same surface conditions, same material. Everything is pretty much constant over that time. So a lot of the variables that occur with manual UT are addressed with the permanent installed sensors. They have a pretty wide range of temperatures they can be used at, and the key thing here is you can get a reading just about any time you want. So instead of getting readings every 5 years or 2 years or whatever, you can get a reading every year, every month, every day if you like, every hour if you like, but I don't think that would be realistic either. And because you have more data and more information, you have the ability to identify corrosion issues at an earlier stage. So once you know that a problem is developing, you have more time to take a plan of corrective action, whether it's changes in the process or planning a replacement during a turnaround or whatever. The earlier you can find it and identify it, the more time you have to address it. And with that kind of information, you have a much better ability to manage your corrosion problems. You can identify things that are causing the corrosion erosion issues in the process by having more data more often. It gives you the ability to safely acquire information about the conditions, and the consistency and reliability of data is very good. So permanent sensors have a lot of pluses that they add to this technology that eliminate some of the problems we've experienced in the past. So basically what we have is a transducer connected up to a wireless node, which can handle 4 transducers and 4 thermocouples. And it ties into a network. Many locations now have implemented wireless networks within their facilities. The most often in oil and gas is one that is based on HART technology. It's proven to be very reliable and has several factors in its favor. So the most often used is the HART platform. There are needs to either, as I said, tie it into an existing network that's already been installed or tie it into a new network. If there's no network installed, then there are some issues that have to be addressed as part of the installation and setup. And these have to do with usually IT and safety and process people, just kind of a whole checklist of installing a network. But in either case, the existing network or a new network can be implemented to handle the information generated by the smart sensors. So networks allow plants and operators to use the Calibre system, as I said before, to improve the transfer of information and conditions, retrieve the data from each sensor, and streamline a connective pattern. So what we're talking about is basically picking back onto existing networks or setting up a new network to handle the new data and the new information. This is the type of networking that usually goes on. It's called a wireless mesh network. And what it does is allows any sensor on the network not only to transfer its data that it's generating, but it also acts as a relay station for any other sensor that's operating on the same network, even though it's a different technology. So what happens is, even though we don't have line of sight from a given sensor back to the gateway which handles the traffic coming in from the sensors, As long as there is line of sight to another sensor on the network, that particular sensor can pick up the data and transfer it over to the gateway also. So what the mesh network allows us to do is install sensors a great distance from the gateway that's handling the traffic for the network, and allows us to have more flexibility in how the positioning is utilized when installing the sensors. There is a little bit of effort sometimes when distances are fairly long. In those cases, there could be a need for a repeater to be installed, but for the most case, what we're looking at is the various transmitting devices in the network transmitting their data plus any other data that needs relay because of obstacles or distance or whatever. So the wireless mesh network is between the sensors and the wireless gateway. The wireless gateway collects data and handles basically the traffic that is coming in from all of the sensors on the network and sends it back to a logging system, which could be a DCS, could be another computer, whatever is set up on the network to handle all of the data. But there are a number of advantages to this approach for using the wireless technology, and so that's what we have chosen to do with the Calibre system, allowing it to handle data from other sensors as well as the data from its own. So, as I said, Calibre is designed to provide users considerable cost savings and enhanced operation to avoid major incidences. So, what we're looking at is having more data, more information to have better maintenance and planning schedules. If we detect something at an earlier stage, we are better equipped to handle the problem. It allows plants to implement corrosion management and preventive maintenance programs. When you know you are developing a problem, you can minimize the downtime because you're dealing with a known problem as opposed to an unexpected problem that could have occurred. And so the cost of doing those types of repairs generally is much less and can be handled in a better manner. On the bottom, as I noted, it does have the ability to handle 4 sensors. Sensors are mounted by mechanical devices. They can be mounted circumferentially at a given point, like an elbow, or they can be spaced out along a pipe or a vessel so that you can get multiple single points as opposed to a measurement in a circumferential manner. It also has 4 thermocouples so that when we are measuring, using it at higher temperatures, the maximum it's rated for is 350 C. We get separate measurements for the actual temperature, and we can then compensate the temperature measurement with that temperature value. So we do take that into consideration when we're doing high temperature work. This is a typical high temperature installation. On the left-hand side, you'll see the surface prep, and the transducer is mounted dry. We do use a thin metal film material as a coupling material because the surfaces still require some sort of coupling material. And so we try and get as good a smoothest on the surface as possible. The sensors are then mounted in the housing, and the housing here is then clamped to the pipe using these straps. The housing here has a spring, which is putting pressure on the transducer against the pipe, and it's torqued down while we're measuring with the thickness gauge to get the proper reading. So what happens is when it's installed, you torque down on the transducer while it's connected up to a D meter, and you get the appropriate thickness measurement at a certain torque loading, and then that becomes the value. There are some of the places that could be installed: overhead crude lines, injection points, elbows, reducers, basically any place where you have concerns about corrosion and erosion that you want to have more data so you can get information earlier, and you can also have better planning for addressing problems once you know that they are occurring. So the installation is fairly simple. As I said, they get mounted using that technique, and then connected up to the node, which transfers the information. This just shows here is the thermocouple connections. These are the sensor connections here. These are the thermocouple connections. They are separate devices. And on the right-hand side are just some typical installation connections. This is on a horizontal pipe, and the instrument here is strapped around the pipe in that particular manner. This is a vertical pipe here. This is a separate installation. This is a vertical pipe here. And again, you see it mounted with the straps going this way, and then the sensor connections coming in at the bottom of the pipe. So it's engineered for non-intrusive and permanent installation on piping and pressure equipment. And installation is usually handled by MISTRAS personnel. The fact that we have a large service organization and they are on site on many locations, we have access to a large workforce that can assist in not only installing these, but assist in the maintenance of these units should any kind of problems develop. So we do handle most of the installation work. It is sometimes an issue depending on whether there's unions involved or no unions and things like that. But for the most part, we can at least be responsible for the electronics installation, if not the whole thing. At this point, I'm going to turn it over to Larry, and he's going to handle some of the software and online monitoring capabilities of the Calibre.
Thanks, Sam. As you can tell, using a remote thickness tracker like the Calibre gives you a lot of applications and opportunities to collect a lot of thickness data. Now, what do you do with that data? There are a couple different systems that we're able to interface with, IDMS type systems. These are integrated database management systems like PCMS, like Meridium, Capstone, UltraPipe, things of this sort. So it's the Calibre itself is equipped with a combination of advanced software and online monitoring suite that gives your operators quick, up-to-date, real-time thickness data that can be compared with past conditions for trending and things of this sort. PCMS is one of MISTRAS's products, and So its functionality gives you the capabilities of looking at a corporate dashboard, as you can see, showing either a corporate-wide setup or drilling down to individual facilities for information, not only corrosion information, but some of your other functional information that you would need. Gives you the not only your corrosion calculations, but also your RBI calculations that are going to give you your probability of failure, consequence of failure, automated damage mechanism screening, and of course your target dates. The web-based software that comes with the system, if you're not using one of these IDMS systems, gives you a lot of capability to not only view the location of the different nodes and the TMLs, your thickness measurement locations, but then also data about each individual TML. And we'll go through those here shortly. So here you're looking at a screen that's showing you different node locations, each having its own name, serial number, things of this sort. And it's giving you a nice overview of what's happening in your plant at this time with each of the TMLs located within each node. So if we drill this down a slight bit further, we can actually look at data that was pulled from one individual node and one individual TML, showing you actual trending data over a given period of time. So you're able to choose your start range and ending range to produce the trending data. What you can also do is overlay temperature data at the same time to see a nice correlation of what exactly happened as temperature changed. Did your corrosion rate increase? Did it decrease? So that data can be correlated and viewed directly on the screen itself. Now, for each node, typically comes with 4 sensors. You can also view all 4 of those trends on the screen at the same time instead of having to view them separately. So it's kind of a user choice on how they would like that data set up. And as Sam mentioned earlier, each node can be set up to take data, typically 1 reading a day. That can be changed as necessary to, if you've got an area that you really need to monitor more so, it can be set up on once every hour or whatever the case may be, and then you would be trending additional information. And what you're also able to do with that data is we can export it directly to PCMS or any of the other types of IDMS systems for doing further RBS type work. Now, when you're doing analysis of thickness data, corrosion data, and you get a jump or a loss of material, you typically want to analyze that particular area or that particular reading. And the only way to do that is to look at a waveform. So we do have the capability of going to a certain area, picking out a particular waveform, and seeing exactly what's going on. Here you see a typical full wave waveform. You can see the gate stated across at about a 40% screen height level. And based on this particular waveform, I've got a great signal. I would look at that data as being accurate data and continue on with the monitoring. What this also does is if for whatever reason you get some questionable data and you look at a waveform, it could actually be an installation problem. It could be, something in the system may have a problem. So this is an excellent way of being able to evaluate what's going on at that spot with that particular transducer. And of course, looking at a waveform is going to enable you to do this. We can look at this waveform as either an RF, your full wave signal, or we can look at it as a full wave signal with your 0 point down at the bottom. This particular graph is showing us percentage of screen height in the vertical, and then we're looking at microseconds on the horizontal. This can be adjusted to either read out in microseconds or in thickness data. Some of the features and advantages of the system, many of these Sam went over, but we'll go over a few of them just to make sure. It is a non-intrusive design and installation, which means we don't need to shut down the plant to install the systems. Material can still flow through the pipe as necessary. We get highly precise readings. When we do the installation, we do set it up. We use an instrument, flaw detector, thickness gauge, typically to set it up, calibrate it so that you are getting very precise readings. It does have high temperature functionality, as Sam related, up to 350 degrees C. The system itself, the network, is self-organizing and self-healing. If you have an area that, a node that goes down, the system itself will heal itself by finding another path to transfer that data to the gateway. You have increased reading intervals that can be adjusted by the user as necessary. Definitely improved corrosion management. That's without a doubt. When you have more data, it gives you a lot of opportunities to manage that data and manage your corrosion. Also has reduced installation costs. No welding or things of this sort are necessary. We use a single channel pulsar, 4-channel multiplexer. We've got a 70 dB gain range and an 8 megahertz bandwidth. On the Calipray system, we do use a square wave pulsar, which most of your instruments today that are doing corrosion monitoring are using square wave pulsars. Smart sensor network for wireless communication. Ultra low power, up to 5-year battery life, and that's typically taking one reading a day. And the big one, it is intrinsically safe. Class 1 Div 1 and also ATEX for our European brothers across the pond. The system itself comes with all mounting brackets as necessary for the Calipray node itself, plus mounting for both high temperature and low temperature sensors, along with installation guides, monitoring software, and the such. Most systems are, of course, going to be fairly custom for the most part, depending on what the operator's needs are. So typically a walk down is what will be done before purchase so that the system can be laid out accordingly with a combination of either low and high temp sensors or just one or the other. That's about it for the presentation. Definitely visit us at www.calipray.com. The entire system is manufactured right up at Princeton, New Jersey, at our world headquarters. So with that, I thank you for your time. I think Sam's going to look at a couple questions right now and go from there.
Thanks. Thank you, Larry. I have a few minutes to pick up a couple of questions that I'll answer now, and the rest we'll answer through emails. One question comes from Bruce Pellegrino at SNI, and Bruce asked, can you ping the installed UT sensors to take T readings on demand? Yes, you can. There's two ways it can be handled. It can be handled either with a handheld setup instrument, or it can be handled through the web-based software. So if there was a situation where you wanted to check a particular sensor, you can ping it on demand in either of two ways. Another question is from I gotta put my glasses on. Old age has nothing good to my eyesight. Jeffrey Jorgensen from, I'm sorry, I can't read, it's too small. But basically wants to know the maximum frequency of receiving data points. The wireless network requires the units to talk to it every 38 hours as a maximum. That's to make sure that it knows it's still out there, that it is still alive and working. So the maximum interval for pinging and getting data right now is controlled by the network. That's typically about 38 hours. Leonardo Cardenas from KBC asks, is this for Spot UT? Yes, it is. Actually, there were two questions along those lines. It is Spot UT, so each sensor is taking a measurement at that particular point. There was another question asking if it could be used with pins or GUL collars. Unfortunately, not at this time. Right now, we are limited to looking at single spot transducers, and if we can find somebody with some deep pockets, maybe we can come up with a version that works with a guided wave collar or pin. That's about it for now. I'm going to turn it back over to Brady, and he can sign off.
Thanks, Sam, and thanks, Larry, also. And thank you all for attending today's webinar. You can view it on demand starting tomorrow at bicwebinars.com. We encourage you to share it with your colleagues on social media, LinkedIn, Twitter, Facebook. And we want to thank, once again, Mistras Group for this webinar. Have a safe day.